Hey everyone, welcome to another episode in Physics is Fun. Today is going to be about conservation of momentum and its relationship with energy. Let's jump into reading the question. Two blocks are free to slide along a frictionless ramp. The block of mass m1 equals 5 kilograms is released from the position at height h equals 5 meters above the ground. A North Pole magnet protrudes from the block and will repel the North Pole magnet of the mass m2 equals 10 kilograms, which is at rest. The two blocks never touch, so calculate the maximum height m1 rises to after the elastic collision. Now let's move on to drawing the picture. There is a ramp like this with mass m1 right here at the top and m2 down here at the bottom. The height of the ramp is h, and I drew uncarefully and measured h to be below the bottom of the ramp instead of at the bottom of the ramp. With the picture drawn, let's figure out what we need to do. This problem states the collision is elastic, so let's write the elastic equation down of v1 final equals m1 minus m2 over m1 plus m2 all times v1 initial plus 2 times m2 over m1 plus m2 all times v2 initial. We are only calculating for the one mass, so just this one equation will work fine. We are only given a mass and a height in this problem, and since this is elastic, remember that kinetic energy is conserved. So this equation is coming from kinetic energy final equals kinetic energy initial, since there is no change. We can also use conservation of energy for the relationship of mass, height, and velocity. Thinking a bit more, our second mass does not ever move, so its velocity is actually always 0, so v2 initial equals 0. Since it is 0, this whole right term goes to 0, and I cross it out, and also erase it since we do not use it for this problem, leaving just v1 final equals m1 minus m2 over m1 plus m2 all times v1 initial. Now we only have one unknown in the equation, which is v1 initial. So we need to split this problem in half, finding the velocity at mass m2. In this half, this final velocity will become the initial velocity for the second half. So to find this final/initial velocity, let's use conservation of energy and solve for that. With the equations set up, it's time to calculate. Reworking with our conservation of energy, rewrite the work of non-conservative forces equals the change in kinetic energy plus the change in potential energy. Writing out the changes gives kinetic final minus kinetic initial plus potential final minus potential initial. And add both kinetic initial and potential initial to both sides, crossing out the right, leaving just k initial plus u initial plus the work of non-conservative forces equals k final plus u final. We have no work of non-conservative forces, so that all goes to 0. Now expanding out the equation to get 1/2 m1 times v1 initial squared plus m times g times h initial equals 1/2 m1 times v final squared plus m times g times h final. Somehow I completely flipped the initial and final values here and did not double check for this part, so bear with me. Remembering this part is only half, some terms that are 0 are what should be the final height and initial velocity. Again, I flipped these, so I made the initial height 0 and final velocity 0, but this isn't quite right and should be done the other way. This still does give the right answer we need, but not the right variable and from the wrong calculations. So moving on and crossing out what should be 0 leaves with just 1/2 times m1 times v initial squared equals m1 times g times h final. Multiply both sides by 2 divided by m1 and cancel both on the left and cancel m1 on the right. This leaves velocity initial squared equals 2 times g times h final. Square root both sides to finally get the velocity initial equals the square root of 2 times g times h. Now remember, this should actually be the velocity final for this half, which does turn into the velocity initial for the next half, but again, I calculated this part a bit wrong. Now we can find the final velocity after the collision by plugging in the velocity to the equation. Rewriting v sub 1 final equals m sub 1 minus m sub 2 over m sub 1 plus m sub 2, all times v sub 1 initial, which is square root of 2 times g times h. Now we can just plug numbers in and solve. So 5 kilograms minus 10 kilograms times all of square root of 2 times 9.8 meters per second squared times 5 meters, all divided by 5 kilograms plus 10 kilograms. This gives a final velocity for mass m sub 1 equals to negative 3.3 meters per second. With our known value for the velocity, we need to find the height now using the relationship in conservation of energy. Rewriting k initial plus u initial plus work sub nc equals k final plus u final. We have no work done again, so that goes to 0 and gets crossed out, and expanding gives 1/2 m sub 1 times v sub 1 initial squared plus m times g times h initial equals 1/2 m sub 1 times v final squared plus m times g times h final. Let's go over the variables again due to my confusion. So the initial velocity and initial height for this half comes from the final velocity and heights from the first half, which I happen to write as the initial, not the final. But this turns into the initial for the second half. Also, with this half, the block goes up and stops at a max height, so the velocity final will equal 0. So with this in mind, the initial height will be 0, and the final velocity will be 0. So cross those out and going to 0. This leaves 1/2 m sub 1 times v initial squared equals m sub 1 times g times h final. M sub 1 is on both sides, so can cancel those out to get g times h final equals 1/2 times velocity initial squared. To solve for h, divide both sides by g and cancel on the left side to get h final equals v initial squared divided by 2 times g. Plug in numbers to get negative 3.3 meters per second squared divided by 2 times 9.8 meters per second squared, which equals 0.55 meters. So the final height the mass moves after this collision is 0.55 meters high. After seeing this problem requiring two halves, the first half gave us the velocity of negative 3.3 meters per second from using conservation of energy to plug into the elastic equation. Then use that velocity to start the second half and find the object only goes 0.55 meters high using conservation of energy again. I hope these intro problems are as helpful for you as they are for me. Thanks so much for watching. Hope you come back to learn more exciting material, and see you next time.